Today we're going to be going over intriguing properties of vision transformers. In this paper, they wanted to compare transformer models to CNNs, namely VIT, DEIT, and T2T on a variety of tasks. So they performed 5 main experiments. The first was image occlusions, and they found that the transformer models were more robust against these occlusions. Next was their ability to model shape, that is to correctly classify an image based on shape rather than texture. And in some instances, they found performance of the transformer model was comparable to humans. They wanted to test the effect of positional encodings on the global image context. They found that positional encodings were not quite as important as previously thought. The effect of perturbations on the input images and how they affected the classification. They found that transform models were more robust and not as robust in certain situations. And then the effect of the off-the-shelf tokens for downstream tasks, and they found they were generalizable. So first experiment, are they robust to occlusions? So how do they create an occluded image? Well, they have an original image like this. They divide the image into 14 by 14 patches, or sorry, a 14 by 14 grid of patches. And then they do what they call patch drop, which is simply if a patch is selected to be dropped, its pixel values are changed to 0. And they have 3 main methods for deciding which patches to drop. First is random. They simply select a random subset, like down here, random subset of patches, and then those patches create kind of a mask. They're dropped, they're turned to 0. Salient patch drop, which focuses on the foreground image. They use the self-supervised dyno model, which has been shown good for separating out foreground pixels. And they use this to determine, by setting a threshold, to determine which patches contain the most amount of foreground information. And then those patches are dropped as seen here. So like the birds patches will be dropped, and then the background is what remains. And then non-salient patch drop is the opposite, where if they're below the threshold, those are dropped instead, and that results in the background being masked and the foreground being present. For this experiment, all their models were pre-trained on ImageNet, and then they used the ImageNet validation set of 50,000 images with the masks applied to them. For random patch drop, they report the accuracy of the mean accuracy of 5 runs. For these salient and non-salient patch drops, because they're deterministic, they only need to report the accuracy of 1 run. So for this, instead of focusing on details, we're going to look at the general trend. Here they've tested 4 different CNN models on random patch drop. And you'll notice that as the information loss increases, the accuracy decreases quite substantially and quite quickly. With the salient or foreground patch drop, you'll notice it has a similar trend. And with the non-salient, which is the background patch drop, you'll notice it's a little more accurate, which makes sense because we still have the foreground important part of the image still present. When they did this, they noticed that ResNet 50 performed the best. So for a lot of their experiments, they compare against ResNet 50. For transformer
Can you say what is information loss? Can you just explain?
Oh yes, information loss. This is basically like what percentage of the patches have been dropped or blacked out or masked out. So the more like, so 0 would be the original image, whereas 100 would be there is no image at all. It's all black pixels. And so like 50 would be half the image has been either randomly dropped, or the foreground has been dropped, or the background has been dropped.
Okay, good.
Okay. For transformer models, here we have DEIT. Notice they use different sizes, base, small, and tiny. You'll note that overall, it doesn't matter what size the model is, it is vastly outperforming the ResNet model. Also notice that it has kind of this convex curve, meaning that as the information loss increases, it's still retaining a lot of its accuracy despite a lot of the picture being masked out. For salient or foreground, we see that same kind of dip where it becomes a little less accurate because, again, that's the foreground part of the image being masked. And for background, we have the best accuracy curve because it's the background that's missing. The rest of both the T2T and the VIT graphs aren't included in this presentation, but they do exhibit the same trend as DEIT. All right. So they wanted to know how the attention mechanism is affecting is affected by this masking. So here you have an example mask of an image. And this would be a random patch drop where the white squares would correspond to patches that are still being looked at. They're non-included. The black portions are drop patches that are being included. And if we look at the first attention layer at the some attention maps, you'll notice that the output, the attention is being focused on the image as a whole. So these would be the output of different attention heads. This is not all the heads, just some of them, but overall the attention is being looked at as a whole. Whereas when we get to the last layer, layer 12, you'll notice that the masked portion is pretty much being ignored and all the attention is being focused on these unmasked portions of the image. So seeing that, they said, okay, well, when we're occluding an image, how much information are we losing here? Is there any kind of correlation between the class token of a non-occluded image versus an occluded image? So they ran a correlation. They calculated correlation coefficient between U and V, where U is the class tokens of the non-occluded images, and V is the class tokens of the occluded images over the whole data set. And they averaged these after normalizing these. And they normalize by subtracting the mean of those class tokens divided by the standard deviation. And that gives you a number that is between -1 and 1, where -1 is an perfectly inverse correlation, which you won't see here. 1 is a perfect positive correlation and 0 is no correlation. And you will see with a random patch drop of 25%, 50%, and 75%, the feature maps of ResNet from the non-occluded to the 25% occluded, 50% occluded, they get gradually become less correlated as we go along, meaning they're not really focusing on the same things. Whereas all these transformer models maintain a much higher correlation between their class tokens, between the non-occluded and occluded images, showing that they are doing a much better job of focusing on these, staying focused on these features. In this graph, you can see this is a 50% random patch drop. You can see a big difference between the transformer models up here and the correlation with the ResNet model down here. And these are the 12 superclasses of ImageNet. And they're also just showing that there's no one class that's skewing these correlation results. That doesn't really matter what class it is, as long as you're looking at the same model, the correlation results are still holding fairly equal. Okay, they also wanted to know if they can model both shape and texture with transformers. And why do they decide this? Well, a paper they cite stated that CNNs are base more of their decisions on the texture of an image than the shape of an image. And as an example, when presented this image, a ResNet 50 said that is an elephant. When presented this image, it said that was a cat, but when you overlay the shape of the cat over the elephant skin texture, it identified this as an elephant. And that paper overall found that CNNs tend to identify based on texture, they're biased towards it. So in that paper, they developed a data set called Stylized ImageNet, which we'll go over in the next slide. And that can be used to both test for shape bias and to also train a system to pick out shape features. This paper notes, though, that they did not use augmentations because that would destroy some of the shape data. So all Stylized ImageNet is you take an image from ImageNet, you perform a style transfer on it, kind of creating these different styles of art pieces. The important part here to note is that in these stylized images, the general shape of this lemur here is present in all these images, but there's no real textural cues to use because they're all different and it doesn't really retain a lot of the texture of the original image. So what this resulted in when testing, shape bias, all shape bias is correct predictions made, a proportion of correct predictions made based on shape. So you'll notice here that ResNet 50 has a lower shape bias than all these other transformer models right here, which are just trained on regular ResNet. However, when we train on SIN, the Stylized ImageNet, the shape bias for all three of these goes way up. And the transformer models actually outperform ResNet with pre-training on this SIN data set. Another thing to note that's important here, if you look at this graph, these little purple dots here represent humans. And all this is showing over here on the right side of this graph corresponds with identifying things based on their shape versus their texture, which is on the left side. So as humans, we tend to identify objects based on their shape more so than their texture. So like their silhouette or the outline of the shape. Well, when DEITS trained on SIN, which is this red pentagon here, it approaches or exceeds in some cases the preference to identify based on shape. So that's good, but the authors wanted to strike a balance between identifying using shape features and texture features. The problem with the transformers is that they were focusing too much on shape. So they introduced shape distillation. All this is the DEIT model that uses a ResNet 50 pre-trained on SIN as a teacher. That's the stylized image net. It operates much the same. You have your patch tokens and you have your appended class token and a new shape token here that passes through the transformer blocks. The output of the classification head has its cross entropy loss computed against the label. The output of the shape head has soft distillation loss computed against the softmax of the ResNet teacher. And what they're showing here, they have both tiny and small SIN models, but you can see that when trained on SIN with a class token but no distillation, there's a high shape bias and low accuracy. Then when you distill the class token, you get increased accuracy, but at the cost of the shape bias, which they wanted to keep. So then by introducing this shape token that is distilled, you do lose some accuracy, but you increase the shape bias and you have a more balanced approach than either of these. So knowing that the transformers were good at identifying shapes, they also found that this could be useful for automatic image segmentation. So what that means is they can use the output of the attention map, the final intention map, and they can create a mask from it like so. So here you have the small DEIT, and you can see a lot of the patches or the patches are corresponding to the image in the foreground. Then when they add the training on the SIN, it's much more focused on the image in the foreground. And then by including the distillation token, it is a lot of this excess noise from the background is gone, and it is more easily segmented into its position, into its pieces. This mask can be performed intersection over union with the ground truth to create what's called the Jacquard index. And we see by implementing these extra things such as the training with SIN and then including the distilled class token and then including the distilled shape token, we increase this rating, which makes it better. I will stop sharing.
You can see my screen?
Yes.
Okay, so you can see my cursor? Okay. So the next question that the authors of this paper decide to ask is, do positional encodings preserve the global image context? So quick refresher is that an image is a collection of pixels, and the position of those pixels is significant in that they tell global information about the image in relation to all the other pixels within the image. So this information is definitely very important for an image to maintain. So as we remember, transformers are sequence invariant, meaning that no matter which way these patches are put in, the actual output of the transformer does not change. And so as we remember, the authors add a positional embedding, which imbues that global information into the image, or so they say. The authors of this paper try to see whether or not these positional embeddings actually are maintaining the global context of the image. So the way they decide to do this is using a shuffling occlusion technique. So if this is the original image, this would be a 2x2 grid shuffling technique where the image is split into 4 patches. And the thing to note here is that the less patches that the image is split into, the more global context is maintained. So as you can see, you can kind of tell that this is still a person, even though they've been shuffled. But as you increase the grid size, you lose more of that global context. So the idea is to see how the vision transformer will perform when the image is corrupted more. And so the main research that they performed was to train the ResNets and a CNN, or the ResNet CNN and the transformer models normally, and do the transformer models with positional encodings, and they're trained on the natural images. But when during the testing sets, they apply different levels of shuffle grid size and see if those accuracies are still maintained. So as you can see with the ResNet model, which has low positional invariance, what you tend to see is that because it was trained on natural images, as you increase the shuffle grid size, the accuracy of the model plateaus. But that isn't necessarily the case with the DITE models, which implies that these positional encodings present within a transformer model might not actually be doing the including the global image context within the image in the same way that a CNN might. Another thing to note as well is that when the patch sizes are equivalent to the amount of patch, or the shuffle grid sizes are equal to the number of patches that the transformer was trained on, you see a sudden increase in accuracy. And that is because when they're both the same, it can be seen as just a reordering of patches, which we know transformers are able to handle. Another thing that they tested is what happens if you remove the positional encoding altogether from a transformer model. And the first thing to note is that on the natural images, on the testing set, including natural images, the accuracies are relatively similar, which implies that the positional encodings really don't provide that much of an improvement over when there are no positional encodings, and that it's still able to train effectively, which implies that the positional encodings aren't even necessary for classifying an image correctly. And as we can also see, the non-positional encoding transformer actually maintains better positional invariance, which means that with the positional encoding in a transformer, it doesn't seem to be doing much at all, because it doesn't provide the global context. It doesn't provide a significant increase in accuracy for natural images, and it loses a lot of that that permutation or that positional invariance. So the last thing I wanted to look at is they wanted to look at how much the patch size provided with the model actually affects the accuracies of when applying different levels of shuffle grid size and corrupting the image. And they showed that with a higher patch size, the image actually performs better in general, which isn't too surprising. As you can see, on natural images, higher patch sizes tend to perform better. And then as before, when the shuffle grid size equals the amount of patches trained, there's a slight bump in accuracy, where in this case 64 patches performs better than 196, and then in this case the same thing happens with the 196 grid. And so from this we can conclude that the main factor for determining how well a transformer architecture, or vision transformer architecture, can handle some kind of occlusion, in this case shuffle grid, is actually the amount of patches being provided to the architecture. And so the final takeaway conclusions is that, first of all, vision transformers show high permutation and variance to patch positions, which is something that isn't very surprising when you consider that they are sequence invariant. The next thing I wanted to highlight is that the positional encodings that we currently use for vision transformers do not preserve the global image context, and that it implies that maybe we don't understand what exactly the positional encodings are doing as well as we hope that we would. And so maybe, and it also implies that maybe we need to provide further research into how to handle these positional encodings. The next thing is that the dependence on positional encodings to perform well under occlusions is also incorrect. And as we showed when comparing the two transformer models with and without positional encodings. And finally, that the VIT's robustness to these occlusions is a result of the dynamic receptive field that James explained earlier during the patch drops, and that the patch size is the main determining factor for whether and how well a model will perform under these occlusions. And so that it's the end of my section, and I'll pass it off to to Joe.
Okay, let's see. So I'll be talking about the robustness of VIT to adversarial and natural perturbations. So robustness to natural perturbations. The question is, are VITs robust to common corruptions like fog, rain, snow, and noise? To evaluate this, there was a variant of ImageNet called ImageNet C for corruptions used as a baseline. There were 15 common augmentation methods seen on the right here, including noise methods, blur, snow, frost, fog, brightness, and other various types of data augmentation methods. There were 5 levels of aggression that were used to do this type of augmentation, which I'll explain in a minute. These were all hand selected, so there's no, they were just all hand selected values for how aggressive each operation was. And these augmentations are only applied at test time. So it's testing how well the model performs under all these conditions without these augmentations in the training set. So the way that the authors scored different models using this technique was first computing an error, a test error E on a specific model for each corruption method with each severity. So for example, you would evaluate a VIT model on the snow corruption using severity level 5. And then each one of those errors was summed across all of the severity levels and then normalized by a common baseline. The authors in this paper didn't exactly say that they used the AlexNet baseline, but it doesn't really matter which one they used as long as it was common across all of the corruptions. The point of the normalization is just to ensure that if one corruption type was much more severe to an algorithm's performance, that was kind of normalized out by this step here. So they averaged the scores across all of those different corruption types to get this mean corruption error. So what does it look like? Again, this is a relative metric, so lower is better. When we look at models trained with data augmentations, augmix is our baseline model here. This is just a ResNet 50 trained with a specific augmentation strategy. We find that most VITs trained with data augmentation perform better than that baseline. So again, 65 for the common ResNet model with lower scores across most other vision transformer models. In contrast to that, the VIT SIN models were found to be more susceptible to these natural distribution shifts, even compared to a regular CNN ResNet 50. So you can see 76.7 here versus a small deviation for the SIN model of the same ResNet architecture, but much higher scores on the DITE models. And this just supports that there is a huge trade-off between shape bias and robustness. Moving on to the adversarial patch attacks. Adversarial patches are taught to confidently confuse a classifier. Like some real world use cases would be confusing autonomous vehicles with road signs. So instead of understanding what the true road sign is, if it was like a speed limit or a stop sign, these patches are applied to that stop sign or that sign to confuse it. It could also be used to trick facial recognition software. So for example, we have a classifier looking at this banana here. We see that after the softmax, it's predicting a high confidence score for banana. Once the patch is applied or placed in the real world and another image is taken here, the classifier is now highly predicting it as another class. So a quick overview of how that's trained. The adversarial patch is derived by applying a random patch and then optimizing for the classification output of a provided class. It could also be untargeted, in which we're basically just maximizing for the loss of the true class. So instead of trying to minimize that this image is a dog here, we're trying to maximize that it has the most loss possible, and we predict anything except dog. So it takes into account the location of where the patch is placed, the rotation, scale, other factors like that, as well as the original input image. And that is how the patch is regressed from noise. So looking at the robustness of this adversarial patch attack, they looked at a few different models and compared the top one accuracy on ImageNet with respect to that patch size. As we can see here, most of the DITE models performed much better as compared to the baseline ResNet 50 models, showing that these transformer models were much more robust to this adversarial attack. And another thing to note is that this type of attack is unbounded for the basically how far we're changing the pixel values away from what the true pixel value is supposed to be in the original image. We'll explain why that's important in the next slide. Again, as we just saw, when looking at the sign models instead, the ResNet model actually performed slightly better than its relative DITE models, although we are looking at much lower top one accuracy scores as compared to the left-hand side here. Another type of attack that the authors evaluated was the FGSM. So this is a fast gradient sign method used to generate an image, again, that maximizes loss with respect to the true class. So in this case, noise is applied to the whole image rather than just a patch. And the change in pixel values is bounded for these attacks and white box. So the method is summarized here, where we have the original pixel in the image. We have some epsilon value, which we're going to use to budget how much each pixel could be changed in either direction. And then we're just using the sign of the gradient computed from the network itself and the loss function to determine which way we're going to move that pixel. So this could be, say, if this was pixel value 10 and E was 5, we are either going to move plus or minus 5 pixels or plus or minus 5 values for that pixel. So looking again at the top one accuracy scores versus that epsilon value, for low changes in that epsilon, we see that the DITE models again perform much better than the compared to the ResNet 50 model. And then on the right side, again, we see a strange relationship where the sign models for ResNet actually tend to outperform the respective transformer models. Again, there is a huge drop-off in accuracy compared to the models that were trained on ImageNet versus the sign models here, which we're basically looking at noise. And that's it for my section.
Are you able to see my screen?
Yep.
Okay. I will be explaining here effective off-the-shelf tokens for vision transformer. So this picture shows this picture is showing that each block will generate the class token. So that is the characteristic of a vision transformer model. It will because based on this class token, we can process. This will be processed by the classification head separately. So this classification head, once it is performed, after that, this block we can discriminative this will allow us to measure the discriminative ability of each individual block. So, and this class token each block will generate the class token. So I'm sorry, I am not able to explain. I'll go to next slide. So this is the sample data set which authors did ablation study, and these are the performance captured the numbers, and when they have concatenating the class tokens from 9 to 12 blocks, which previous slide showing as these are the blocks, and from 9 to 12 blocks. When they are concatenating deeper blocks, they will get the better discriminative. It will be more discriminative in the deeper blocks. They concatenate the blocks, the deeper blocks. They concatenate the deeper blocks. When they are concatenating the deeper blocks compared to the whole blocks, they got the better results, which are, if we see 9 to 12, if they performing the concatenation, they will get 73 accuracy and 90 accuracy and the 45 on these three different data sets. So further, they did an application study on these different data sets. In case of the classification, they have used a diet as ensemble, and this diet these application studies compared on CNN ResNet 50, and this is compared to CNN the diet ensemble model is performed better than compared to CNN. Coming to few short learning, also compared to ResNet 50, diet model is performed better, better accuracy. And final conclusion, which is vision transformers perform well on occlusion, distributal shifts and patch permutations, automatic segmentation, and adversal patches and common corruptions, and transferability to downstream tasks. These are the references.